Okay, dear students, you can see on your screen a device, and this device is called CRO, cathode ray oscilloscope. And what this device do, you provide it with the electrical signal, and this device draw. This device has a screen. You can see this screen, and on the screen it makes the graph of that electrical signal. How you provide electrical signal? For example, this electricity which is coming in your homes, it's alternating current, and you take the wires and you put them into this device. And what will this device will do? It will make the EMF time graph of the current which is coming in your home. It will make its voltage time graph. This graph, which is shown on the screen, has two axes. One is the y-axis. On the y-axis, the voltage is represented, and it has x-axis, and on the x-axis, time is represented. So this machine makes the graph of the electrical signal. For example, I can quote you a very good example. For example, if you have a mic, and the wires of the mic you attach with this CRO, cathode ray oscilloscope, and what when you will talk in the mic will convert your sound into electrical signals, and those electrical signals are then fed to this device CRO, and the device will make the graph of your sound here, and it will be a voltage time graph. On the y-axis voltage will be represented, and on the x-axis the time will be represented. It's a very useful device. For example, you must have seen the ECG machine, or in your movies and in the dramas you must have seen when a patient goes into the hospital, they connect a machine with the patient, and this machine gives the heartbeat. The sound of the heartbeat is fed to this machine, and this machine shows the heartbeat of the patient, and on the x-axis the time is represented, on the y-axis the voltage is represented. So if the patient heart is working properly, it will be a sinusoidal wave, and if by God forbid a patient heart stops beating, the line becomes a straight line. And if on the ECG machine the lines become straight, it means that the heart is not beating. So this is cathode ray oscilloscope. We will study about the cathode ray oscilloscope and how it works. We will study the basic structure and basic working principle of the CRO. Okay, here is the basic structure of the CRO. CRO is basically a big glass tube. This is a big glass tube. And this is the screen which was shown you in the previous slide. This is the screen. This portion is called electron gun. This portion is called electron gun. Here we have a cathode. Here we have a cathode, and it is connected with the negative terminal of the battery. And we also have, in this diagram, it is not shown here, but we have a heater here. And what happens when this cathode becomes hot? When this cathode becomes hot, the electrons come out into the air from the cathode. You see, the cathode is a metal, and when it is heated, the electrons which are in that cathode, they come into the air. They come out from the surface, from the body of the cathode, they come into the air. This process is called thermonic emission. This is called thermonic emission. Remember this thing. So the electrons from a heated cathode, they come out into the air. This is called thermonic emission. So here we have an anode, and this anode is at very high voltage. This anode is connected with the positive terminal of a battery, and it has very high voltage. So this anode is basically positive. It has positive charge on it, and it is at very high voltage. So the electrons which are here, they are negative. The electrons which came out of the cathode due to heat, they are negatively charged. And this anode here is positively charged, and it is at very high voltage. So these negative electrons have electrostatic attraction with this positive anode. So these electrons are accelerated towards this anode. Here we have a grid. This grid is basically negatively charged, and we have put it here to stop the excess amount of electrons going towards a node. So this grid is reducing the amount of electrons which are going towards a node. So basically what happened here, due to the thermonic emission, the electrons are here, and due to this positive anode at very high voltage, they are attracted to this positive thing because the electrons are negative. So they start accelerating. So they form a beam. This portion of the CRO is called electron gun. Inside this glass tube, we have vacuum, or you can say very low gas pressure. Inside this glass tube, we have vacuum. And why we create vacuum? Because when the electrons will be moving, if the air is present here, what will happen? The electrons will collide with the atoms of air. And when they will collide with the air molecules, they will be stopped. They will lose their kinetic energy. So when they will lose their kinetic energy, the beam of electrons, which is shown here with this pink color, that will not form. Their path will be hindered. They will lose their kinetic energy, and those electrons will be not able to reach the screen here. So due to the thermonic emission, the electrons came out. This anode attracted those electrons, and because we have a vacuum here, so the electron beam starts moving towards right. This anode has a hole in it. So the electrons pass through that hole and they go straight to this screen. Here we have two plates. We call them deflecting plates. These are called Y plates, and these two are called X plates. These Y plates, they are connected with the electrical signal whose waveform you want to make on the screen. You see what I'm saying? That these Y plates, they are connected with the electrical signal whose waveform you want to see on the screen. So for example, if this top plate becomes positive and this bottom plates become negative, electrons are negative, so they will be attracted to the upper plate, which is positive. So the beam of electron on the screen will go up. If this bottom plate is positive and the top plate is negative, this Y plate, if the bottom plate is positive and the top plate is negative, then the electrons are negative, so they will be attracted towards this bottom plate, which is positive. So what will happen, that on the screen the electrons will go down. So you see, by these Y plates, by changing the positive negative of these Y plates, we are able to move the beam of electron up and down on the screen of the CRO. So these Y plates are basically controlling the movement of the beam of electrons in the vertical manner. So these Y plates, if there are no Y plates, no voltage is provided to the Y plates, the beam of electron will go on the middle of the screen. But if the voltage is provided to the Y plates, then the beam of electron on the CRO screen will move vertically. It can go up, it can go down, it can go up, it can go down. So the vertical motion of that beam of electron on the screen can be controlled by the Y plates. Then we have X plates. So one X plate is on that side and one X plate is on this side. The X plates are also provided with the voltage, and the X plates are provided voltage. The voltage you provide to them is for example, let's say how they work. For example, that plate becomes positive and this plate becomes negative. So what will happen on the screen of the CRO, because the electrons are negative, and if that plate is positive, the electrons will be attracted to that plate. So on the screen, this beam of electron will move towards left, for example, or you can say towards right. And for example, if this side of this plate becomes positive and that plate is negative, then what will happen? The electrons which are negative, they will be attracted to this plate. So when you will look at from here, the beam of electron will move from the center towards the left side of the screen. So you see, by providing the voltage to the X plates, we are able to move this beam of electron from left to right or from right to left. So these X plates, they move the beam of electron horizontally on the screen of the CRO. This screen is coated with the zinc sulfide. When the beam of electron strikes with the zinc sulfide coating, this zinc sulfide coating is called, it's fluorescent. So what happens when the electrons collide with it, it starts glowing. So wherever the beam of electrons is striking, is colliding on the screen, the fluorescent material there, the zinc sulfide there, it starts glowing. So when you look at from here on the screen, that spot's lit up. So you feel that there is light. So you see, again, it's a cathode ray oscilloscope. It's the simplest structure of the cathode ray oscilloscope. It's a glass tube, which is, it has vacuum in it. It has electron gun, and it has deflecting system. In the electron gun, we have a cathode, we have a heater, and due to the heating, the electrons are given out. and we have anode which is positive at very high voltage. It attracts those negative electrons, and the electrons are accelerated. And we have these Y plates. These Y plates are responsible for moving that beam of electron in vertical manner. It controls the movement of the beam of electrons in the up or the down manner. And then we have the X plates. These X plates are responsible for moving the beam of electron on the screen from right to left and from left to right. So they are responsible to move the beam of electron horizontally. So Y plates move the beam of electron vertically, and the X plates move the beam of electrons horizontally. This is called the deflecting system, and this is the basic structure of the cathode ray oscilloscope. I hope that it is clear to you. So the number one, the cathode ray tube is a vacuum glass tube that contains an electron gun, a deflecting system, and a fluorescent screen. The electron gun emits a beam of electrons, that is a cathode ray, which is produced by the cathode. A bright spot is created when the electron beam strikes the fluorescent screen. This is because the fluorescent screen is coated with zinc sulfide, a chemical that glows when electrons strike it. The larger the number of electrons striking the screen, the brighter the spot. Varying the voltage across the Y plates changes the vertical deflection of the electron beam. Varying the voltage across the X plates changes the speed at which the electron beam sweeps horizontally across the fluorescent screen. I hope that you have understood. I have already explained to you all the details. So, when you switch on the CRO, and you will see a dot in the center, and the dot in the center is supposed to be in the center of that screen. So if you switch on a CRO, and this is a diagram of a CRO, and you see you are supposed there's supposed to be a dot in the center of that screen. If and you have connected nothing to the CRO, if you see that the dot is not in the center, then we have two knobs on the CRO. We have two knobs on the CRO which are called X shift and Y shift controls. For example, if the dot, when you switch on the CRO, the dot on the screen is not in the center, let's say it's above the center, then by the Y shift, you can move that dot vertically. With the help of the Y shift control, it's a knob on the CRO. By moving it, by rotating it, you can move the dot, the trace of the electrons on the screen up and down. If the dot on the screen of the CRO, when nothing is attached with it, is either on the right side of the center or on the left side of the center, so you need to bring it in the center. For that purpose, we have X shift control. X shift control is a knob on the CRO, and by rotating it, you can move that dot on the screen to the left or to the right. So whenever you switch on a CRO, and you have nothing attached with the CRO, only the CRO has been switched on, the CRO should show a bright dot in the center of its graph. If it is not there, use the Y shift to move it up and down, and use the X shift control to move it left and right, and bring the dot in the center of the screen. Then we have two controls on the CRO. One is called Y gain, and other control is called time base. The Y gain is actually the scale for the Y axis. You know, the screen of the CRO is like a graph. So on the Y axis of the CRO screen, the voltage is represented. It has squares like squares on a graph paper, and this Y gain is basically setting the scale of the Y axis. It means, for example, if on the Y gain you set it on 2 volt, then it means that 1 square in the vertical manner on the Y axis represents 2 volt. For example, if you set it on 4 volt, it means that 1 square on the Y axis is representing 4 volt. So Y gain is a control on the front side of the screen. For example, this is the Y gain, and it's a knob, and you can adjust it, and it has readings around it. So wherever you set it, that will be the scale for the Y axis of the CRO screen. So by changing it, we make sure that we are able to see the complete wave in the vertical manner. So I hope you understand what is the Y gain. Then we have another thing, and that is called the time base. Let me show you. The time base is here. Time base is basically like the scale of the x-axis. The time base is the scale of the x-axis. I mean, on the x-axis of the CRO screen, the time is represented. So we set a scale that each square on the x-axis of the CRO screen, each square on the screen of the CRO represents how much time. For example, if I set the time base setting on 2 milliseconds, then it means that one small square on the x-axis of the CRO screen represents 2 milliseconds. For example, if I represent the scale, the time base setting on 4 milliseconds, then it means that one small square on the x-axis of the screen of the CRO represents how many seconds? It represents 4 seconds. So one square on the x-axis of the CRO screen represents now 4 milliseconds. So the Y gain is the scale for the y-axis of the CRO screen, and the time base is the scale for the x-axis of the CRO screen. I hope that you have understood this. Because you know the CRO shows a graph, and the graph has 2 axes. On y-axis, the voltage is represented, and on the x-axis, the time is represented. So on the y-axis, voltage is represented, and its scale is controlled by the Y gain. and the scale of the x-axis on which the time is represented is controlled by the time base. I hope it's clear to you. So why guys? This controls amplifies the vertical Y deflection of the electron beam by varying the voltage applied across the Y plates of the cathode ray tube. The voltage across the Y plate is amplified by amplifier circuits in the CRO. Time base. This controls adjust how quickly the electron beam sweeps horizontally across the screen. It does this by varying the voltage applied across the X plates of the cathode ray tube. The internal circuit applies an alternating voltage across the X plates. This varies the frequency of the time base. We will go into further detail in the next slides. Okay. How you measure the voltage? For example, if on a CRO screen, you see a graph, a wave, it will be a shape of a wave. For example, it's in the shape of a wave. So you check that how many squares it has gone up from the mean position, or how much below it has gone from the mean position. For example, if you have a graph, wave-like shape of the voltage graph, so you check how much up from the mean position it went, or you check how much below from the mean position it went. Or if even if you don't have a waveform, if it's a straight line but it's above the mean position, then you count that how much above it is from the mean position. Or if the straight line is below the mean position, then you check how much below the mean position this line is. You count how much squares are there, how much squares it is above the mean position, how much divisions it is above the mean position. You count those divisions, you count those squares, and you multiply that number with that Y gain. You multiply it with the scale of the Y axis. You will get the voltage. Okay? This is how you measure the voltage from the screen of the CRO. The time base is switched off and the voltage to be measured is applied across the Y plates via the Y input terminals. The applied voltage step sets up an electric field between the Y plates. When the electron beam passes through this electric field, it gets deflected. The extent of deflection is proportional to the voltage applied. The gain of the Y input determines the sensitivity of the CRO. A gain of 0.5 volt per division. This is the scale. This is the Y gain. 0.5 volt per division. It means on the y-axis, 1 square or 1 division is representing 0.5 volt. Means that if the electron beam is deflected upward on the CRO screen by 3 divisions, for example, this is above the 3 squares above the mean position, or 3 divisions above the mean position. So multiply 3 with 0.5. So 1.5 volt. So the voltage is 1.5 volt. If you will do questions on this, you will learn it much easier. So we will do questions on this in some later video or during your paper practice. Okay, so displaying the voltage waveform, if we switch on the time base and select a suitable time base frequency, we can display a voltage waveform on the CRO. The voltage waveform to be examined is applied to the Y input terminals. The thing whose waveform you want to see is always connected with the Y input terminal. The number of complete cycles displayed on is given by the ratio. So on the screen, how many complete waves will be shown? That depend upon this ratio. This is called Fy divided by Fx. This is the frequency of the alternating current, which is input in hertz, which you connected with the Y. and the frequency of the time base fx. It's a very important thing. If this ratio is, for example, 2, then there will be 2 complete waves shown on the screen of the CRO. If this ratio of the frequencies is, let's say, 4 or it is 3, then on the screen of the CRO 3 complete waves will be shown. So remember this thing. So here we have uh, you know another, whenever how the CRO is used, whenever you switch on a CRO, you switched on a CRO, you will see this thing. You will see the screen of the CRO, and in the center of the screen, there will be a bright dot shown. So with the Y plates, you have applied no voltage, you have set no Y gain, the time base is switched off, you will see this thing. Okay. If the dot will be in the center of the screen and you have nothing connected with the Y input, if you switch on the time base, then this dot will start moving left to right, left to right, left to right, left to right. So because this dot will be moving as a dot, but it is moving very fastly. So your eye, so your eye will not be able to perceive it as a dot. It will perceive it as a continuous line. So when you switch on the time base, so what happens? This dot will go to the left, to the right, to the left, to the right, and you will see on the x-axis a horizontal line. Okay. Now in this second case, what we have done, we have connected a 1.5 volt DC, the cells, 1.5 volt DC direct current. And the setting of the time, the setting of the y-axis is, the scale of the y-axis is 0.5 volt per division. And the voltage you have connected to the y input is 1.5. So this is the scale for the y-axis. So divide 1.5 with 0.5, you will get the answer 3. So when you will switch on the CRO and you keep the time base off, a dot will appear and it will be 3 squares above the mean position. 1 square is representing 0.5 volt. But this voltage is 1.5 volt, so it will be 3 squares above the mean position. If you switch on the time base, this dot will move left to right, to left to right. On the screen, you will get a perception of a straight horizontal line, which will be 3 divisions above the x-axis. Because it's DC current, the DC current or DC voltage is always represented with a straight horizontal line. And it is 3 steps above the mean position. Vertically, it's above 3 steps above the mean position. And each step is representing 0.5 volt. 3 step means 0.5 plus 0.5 plus 0.5, and it represents 1.5 volt. So this is how the DC current will look when the time base is on and the Y gain setting is 0.5 volt per division. I hope you have understood. Here we have again connected the DC input, and this time I have connected with a negative 2.0 volt. And the setting of the Y gain or the y-axis scale is 1 volt per division. So when you will switch on the CRO and the time base is off, on the CRO screen you will see a dot, and that dot will be 2 steps below the mean position. Because it's negative, so it's on the negative side, it's below the mean position, and because it's DC current, so it will be represented with a dot because the time base is off. So one square is representing 1 volt, so it's 2 volts. So there it will be 2 squares below, 2 divisions below the center of the screen. When you will switch on the time base, this dot will start moving left to right, right to left, left to right, and you will see a straight line, horizontal line on the CRO screen. You see, when you switch on the time base, this thing will be shown. You know, it's a DC current, direct current. Its direction do not change. So that's why you see a horizontal line on the CRO screen, because for negative voltage, it is below the mean position. And because the Y gain setting was 1 volt per division and the input voltage you provided to the Y input was 2 volt, so it is 2 steps below the mean position or the x-axis. Here you have provided, this is another you know, here you have provided alternating current to the Y input of the CRO. You know, the alternating current, its direction is changing. So what we have done here, we have provided with the 20 volt alternating voltage to the Y input of the CRO. If the time base is off, if the CRO's time base is off, when you will switch on the CRO and this alternating current of 20 volt is connected, and the Y scale for the Y axis 5 volts per division. 20 volt, divide the 20 volt with the 5 volt per division. So the answer will be 4. So when you will switch on the CRO, you will see a vertical line which goes 4 steps above the mean position and 4 steps below the mean position. Each square on the y-axis is representing 5 volt. So 20 volt is represented with 4 squares above the mean position, and negative side also 20 volt is represented with the 4 squares. Because you have connected with the alternating current, so it becoming positive 20, negative 20, positive voltage, positive 20 volt, negative 20 volt. So when the time base is kept off, you will see a vertical line going 4 step up and 4 step down. A vertical line will be shown. If on the same time you switch on the time base also, so then the dot, basically it's a dot, it's moving up and down, but we get the perception of a vertical line. And when you switch on the time base, that graph, that dot will start moving up and down, plus it will also be moving left to right. So you will have a dot which will be going up and down, sorry, up and down, and it will be also moving from right to left, left to right, right to left on the screen of the CRO. So on the screen of the CRO, you will see that it's a dot. It's a dot showing up on different locations, but your eye will perceive it as a continuous wave, and you will see this wave. From the mean position goes up, from the mean position goes down, from the mean position goes up, it goes. So this graph represents alternating current. And you can see, because the scale is 5 volts per division on the y-axis, and it's a 20 volt So 4 steps it goes up, and the 4 steps it goes down. The maximum it goes 4 steps up. So on the screen, how many waves will be shown? Here it is given that that alternating current has 50 hertz frequency. So this is the Fy. And in the start of this graph, we were told that the frequency of the current which we are providing to the X plates is 25 hertz. The voltage which we have provided to the alternating voltage which we have provided to the X plates of the CR screen, its frequency is 25 hertz. So divide Fy with Fx. So 50 hertz divided by 25 hertz. So on the screen of the CRO, 2 complete waves will be shown. And you can see here 2 complete waves has been shown. So I hope it's little difficult. When you attempt question on this topic, then it becomes very easy. But I have tried my best to explain to you how this works. Okay, here again, you can see here again in this diagram, you can see that I have provided with the alternating voltage, the with into the Y input, and that will be its waveform I want to make on a CR screen. And the Y gain setting, or we call it the Y axis scale, is 5 volts per division. It means on the Y axis, each square is representing 5 volts. So it's 20 volt. So divided with the scale, you will get 4. So this will go 4 step up because it's alternating. It becomes positive, it becomes negative, it moves in both directions, alternating current. So what will happen? It will go 5 steps up, and it will also go 5 steps down. So on the CRO screen, a dot will appear, but because it's alternating current and it's becoming positive, negative, positive, negative, so that dot is moving up and down, up and down. But this is happening so fast that your eyes, your mind don't perceive it as a dot. You see it as a continuous line, a vertical line. The time base is off right now. In this diagram, the time base is off. So this is moving 4 step up and 4 step down because it's alternating current. So you will see a vertical line going 4 step above the mean position and 4 step below the mean position. The frequency of this current which you have provided to the Y input is 25 hertz. Now you have switched on the time base also. When you switch on the time base, this dot will start moving left and right. This dot is, because it's alternating, but it's moving up and down vertically. And when you switch on the time base, it will move from left to right, from left to right, right to left, left to right. So when these two motions will be combined, that dot will appear on different positions, different locations. But this will be happening so fast, you will see an image of a wave, a continuous wave. So this is representing the alternating current waveform. The frequency of the current which you provided to the Y input, to the Y plates, is 25 hertz. And we know that the frequency of the time base, the frequency of that voltage which you have provided to the X plates is 25 hertz. So divide this Fy with Fx. The answer will be 1. So on the screen of the CRO, only 1 complete wave will be shown. I have tried my best to explain to you that how this whole graph or how this whole diagram works. I hope you have understood. Okay, here I have another voltage time graph. This is called a sawtooth diagram. Sawtooth diagram. Because of this shape, this shape is like the teeth of a saw. You know the saw with which we cut the wood? The shape of this voltage time graph is like the teeth of the saw with which we cut the wood. So that's why this is called a sawtooth voltage. So what we do, this kind of voltage is provided to the X plates. The voltage which is provided to the X plates, on the Y plates, you provide connect the voltage whose waveform you want to make on the CRO screen. But to the X plates, the voltage which is provided in this shape. And this shape is called sawtooth shape voltage. So what happens due to this shape, the display of the electrons, which is represented with a dot, will move from right corner to the left corner of the screen, and immediately it will come back to the right corner again. And then it will go from the right to the left, and again immediately it will come back to the right corner. So by providing this, we are able to move the display of the electrons on the screen. It moves from the right to the left and immediately comes back, and again moves from the right to the left and immediately come back. So this shape, this voltage time graph, is the shape of the voltage which is connected with the X plates or the time base. I hope it makes sense to you. Okay, so we were the uses of the CRO. Yeah, we were talking about in which for what purpose the CRO is used. The one thing the CRO is used is to measure the voltage. I have already explained to you. And another use of the CRO is to make the waveform of the voltage on the screen of the CRO. That's the second use. First use is measuring the voltage. We have already discussed it. The second thing is to display the waveform of the voltage which you have connected to the Y inputs on the screen of the CRO. And the third use is to measure the very short intervals of time. For example, suppose I am standing in a room. Okay. For example, I am standing in a room. For example, I'm standing here. And we make a sound. So this mic will catch that sound. For example, if I'm standing here and I make a sound, so this microphone here will catch that sound and it will display it here. Okay. Then that sound waves will travel, they collide with this wall, they come back, and this mic will catch the echo. It will record the echo, and that will be displayed here. Okay. So you see on the screen of the CRO, my original sound is shown with this graph, this up and down on the graph. And when the echo is heard, this mic heard the echo, it is shown here. So if you know the time-based setting, if you know the scale of the x-axis, on the x-axis of the CRO, the time is represented. If you know the scale of the x-axis, which we call the time base, From here you can count how many squares are between this disturbance and this sound and this sound. Count how many horizontally, how many squares are there, and then multiply the number of squares with the time-based setting. You will get the time lapse between the original sound and the echo. In real life, if this wall is not that far away, the original sound and the echo, they both come in a very short interval of time. So with the help of the stopwatch, you cannot measure the time lapse between the original sound and the echo. But by using the CRO, no matter how small the time lapse is between the original sound and the echo, by using the CRO and the time-based setting, we can calculate that how much is the time between the original sound and the echo. So that's another use of the CRO screen. He has also explained to you, let me read this. Connect the microphone to the Y input terminals of the CRO microphone. Clap your hand once near the microphone. This produces a pulse of sound. It is received by the microphone and shown as a signal on the CRO screen. The CRO, the sound pulse is reflected by the wall. The microphone receives the echo, and it is shown as another signal on the CRO screen. The number of divisions between the two signals can be used to calculate the time taken for the sound pulse to travel from the CRO to the wall and back. For example, if t is equals to 10 divisions and the time-based setting is 5 milliseconds per division, the time taken is 10 multiply 5, and the answer will be 50 milliseconds. So the time lapse between the original sound and the echo is 50 milliseconds. This same diagram you must have seen in the chapter when you studied sound. There they have shown this experiment. They used it to find the speed of the sound. Once you know the time lapse between the original sound and the echo, and you know the distance traveled by the sound to go to the wall and come back, you divide that total distance with the time lapse and you get the speed of the sound. This is in the sound chapter, the use of the CRO. I hope that you remember that thing also. Okay, so here we have the key ideas. The CRO is an electronic device that can be used to measure voltages, study waveforms, and measure short intervals of time. So, my dear students, now we have reached the end of this chapter, and I will advise you to kindly not only see these lectures. When you see these lectures, do one good thing, that always make notes on a copy. And another good thing which you will do is, after watching these lectures, kindly take out your textbook and then read this chapter from the textbook. This is the 22nd chapter of the physics matter, or whatever textbook of physics. If you are a student of O levels, whatever chapter you are, whatever textbook you have, find this electromagnetic induction chapter and read it from the book. It's very, very important. Another thing is very important is that the another thing is very important is that I have in this lecture video only explained you the basic concepts. So by understanding these basic concepts, you are still not in a master of answering the questions in the paper. For that purpose, it's very important that you solve questions on this topic. For in Pakistan, for example, if you are in Pakistan, we have red spot. We have topical red spot. So you can solve the questions on this topic on from your topical red spot, and then you will actually master this concept. I hope that these videos are very useful to you. My name is Ferhan Mazher, and the course I am teaching is Physics 5054. Have a good day, everybody. Have a blessed day. Thank you very much. Bye bye.